And to work with dates and datetimes, we're gonna use the lubridate package. This is also a package from the tidyverse, but it is not part of the core tidyverse packages, so you need to load the package separately with the library command. And as I said in one of the other sessions, you should move the library command to the top of the script, but just because we are entering a new section here, the dates and datetimes section of this video, I'm gonna leave it there. And when we look at the help file for the package, the headline says it, dates and times made easy with lubridate. So dates and datetimes are another set of special data types, and they can be quite tricky in R, but we've seen before when working with the New York flights data that it can be quite important if you want to do some calculations on, say, the arrival and departure time, and you want to know how much delay a specific flight had. So this data time is pretty important, and the lubridate package is there to help you. I don't really know why it isn't part of the core tidyverse. There is some discussion around, but the only thing you really have to remember is that you have to load it separately if you want to work with dates. Or actually what you can do when you only want to change one data type, you can simply write the name of the package and then the two colons to select one special function and then move on, and you don't have to load the package at all if you don't really want to. So what does the package do? So let's say you have a date as a character vector. So for example, here we use the 31st of January 2017. This is no specific date, just something that I used from the book. And the lubridate functions to convert strings into dates all work in the same way. You simply tell the package in which order the individual parts of the date appear here. So here we know that the year comes first, so we use Y for year. Then we have the month, January, so the second letter is M. And we have the day third, so the third letter of the function is D. And this is all we need to do. You can see the help popped up here, and it says transform date stored in character. So we can use this. We copy in the string. And this is all we have to do. On the surface, it doesn't change at all here, but we can save it in a new object here. And when you look at the object now, you can already see that it has this UTC at the end, which is a time zone. And what we can do now is to perform mathematical operations on this. So for example, I could add 1. And what this does is to add 1 day actually. And you can see that the new date is now the 1st of February 2017. As I said, there are a couple more ways you can store a date as a string, and for those, lubridate has other functions. So let's take two more examples from the book here. First, we have January 31st, 2017. This is a common way to write a date. And when you remember, the functions are all just called as the abbreviations of the order in which the individual parts of the date appear. So for this date, we need the month first, then we need the day, and the year comes last. So when we copy this in, this should work. Yeah. Okay, and then the last one, we have the day first, then the month, and then the year. And here we go. What happens if you pick the wrong one? We can quickly have a look at this. So let's say you got confused with this one and you thought the first number here is the day, then the month, and then the year at the end. I mean, it doesn't make sense in this case, but you might get confused with some of the dates. And when I try this now, it tells warning, all formats failed to pass, no formats found, and the result is an NA. And this is basically true. And this is basically true for all strings. So if I type in hello world here, and there obviously isn't a date at all in here, so it still fails and gives you an NA. These are dates for you, and you can use YMD to convert dates where the year comes first, then the month and the day, and so on for the other functions. Then secondly, we have Datetimes, and those work in the exact same way. So let's use the example from the book again. So in this example, we have the year first, then the day, then the month, and then the day. And now we have to use an underscore to indicate that we also have a time here. And as you can see, the hour comes first, then the minute, and finally the second. And when I copy this in here now, you can see that it has been transformed into a time. We can save this as an object. And up here in the viewer, you can now see that UTC was added as before, so you know that this is a date time object. And then let's just use another example. So this is an English time format, which you can see by the forward slashes, and it is missing the seconds here, but that's no problem. What we can do is we can say here the month comes first, then the day, and then the year, which is actually the American way of writing a date. But anyway, and then we only have H and M for hour and minute. Wrap this around the string. And there we go, we have a date time now. And that's basically it when it comes to transforming strings to dates and datetimes. Lubridate can also work with numbers, but only if they are basically representing strings. So for example, we could use the 31st of January here as an example. And if you unquote this and remove the minus signs, then Lubridate can deal with this too, but I would say it is far less useful. The other thing that you might need to know sometimes when converting dates is the so-called Unix epoch, which is simply a specific date in time. So that's the 1st of January 1970. And why is this important? This is basically the way in which R really stores days and datetimes. You can see this by unclassing. So as before, we strip away all the extra information about an object. And when you unclass this, you can see that a date is actually just a number. And specifically, it's the number of days in this case. For datetimes, it's seconds. But here it's days since the 1st of January 1970. We can try this by using date, and then we subtract the number of days that are displayed here. And we get the 1st of January 1970. This is only really important because sometimes you see dates stored as days since this specific date. And just so you know that you can easily transform this back into a date by simply using as date. And again, this is only because sometimes in the wild you find data sets where the date is stored as a single number, and when you check if sdate works and the dates kind of make sense for your specific data set, then you know it is probably the Unix epoch which is used here, which is just a specific way in storing dates on computers. Sometimes dates in datasets are stored as individual components. For example, in the flights dataset, we have a column with year, month, day, hour, and minute. And here those are simply stored as integer values, or the hours even stored as a double, the minute as well, but this doesn't really matter. In LoopRedate there is a function called makeDateTime, and when we use this here to calculate the departure, we simply add the individual components in, and when we have a look at the datetime command, you can see that it expects year, month, day, hour, minute, and second in this order. And it uses some helpful defaults. So if you don't have an hour, for example, it simply uses midnight. If you don't have a minute, it uses minute 0, and the same for second. And you also have to enter a time zone here. We will talk about these later. And when I run this command now, you can see that the departure was converted to S3POSXZT. That simply means datetime. If you print this in the console instead, you can see that the default printing for Tibbles uses DTTM, so datetime. So then to show you why this is useful, let's save this in a new object. Let's call this flightsdt for datetime. And we can directly use this to do some plotting. So use flightsdt, and then I use ggplot. As the aesthetics, I select departure to be on the x aesthetic, and then I use the geom fragplot. So here we go. ggplot selected scale here at the bottom that makes sense. So you see this is now January, April, and so on, instead of individual dates. If you imagine, it would have picked all of the individual date times that are stored in the flights data set. You would have thousands of ticks down here with a very, very small inscription telling you every single point in time when a flight left. But instead it binned this together. So we have January, April, July, October, and January here. So it didn't even select all of the different months. It instead made something that looks nice and still tells you enough about this data. Then I got a warning here, or a message, I think. It tells us that bins was selected as 30. So the values here in the departure are actually stored in seconds. So this means that it binned 30 seconds. We can change this in the book. It used the number 86,400, which is the number of seconds in a day. And what we accomplish here is we bin departure times for one specific day. And this looks like a huge mess now. So what's going on here? Oh, I see. So there are two different arguments. You have bins, which simply says how many bins should be used. And I picked a huge number here. So we have almost 90,000 points in time that are binned together. What I actually wanted to do was use bin width. So how big is the time span for which we combine the observations? And when I use this as a day now, the plot looks a lot better, and we can see that on most days we have around 1,000 flights in the data set, but there are some days in between. It looks like this might be once a month or once a week even, where the number of flights drops sharply. So we have this zigzag line here that tells us the number of flights. And we can see here, for example, there was one date where the number of flights dropped below 500. So if you wanted to analyze this data set, it would probably make sense to look at this date and see what happened there. So what is the difference between dates and date times? Well, first, the thing that I said before here with the number of days since the unique epoch looks a little bit different with date times. So we can use unclass here to show this. And you see the number is absolutely huge because what's happening here is these are seconds since midnight on the 1st of January 1970. So date times are actually stored in seconds, and we can look at this with the mathematical transformations. So what we have here is 11 minutes or almost 12 minutes after 8 p.m. And if we increase this by 1, you can see it added 1 second to this date time. And besides making a date time using individual components, LubriDate can also pull components from a date time. So let's have a quick look at this. We make one date time here, and then we can extract the year with the year command. We can extract the month with a month command, month day, year day, and weekday. And in weekday, there's an interesting argument here, which I think is called label. Yes, exactly. And if you set this to true, it converts the date into a factor, and it displays the abbreviation for the day of this date time and uses the other weekdays as levels in this factor. We can use this to make a plot. So here I mutate the departure which we saved into a weekday, and I added the label true so that each of the observations, each of the daytime observations gets transformed into the abbreviated weekday. You can see the first ones here are on a Tuesday, and it uses, for some reason, the German abbreviation. Not sure why this is happening. Probably something weird on this computer. I usually set everything up in English. But it's a good opportunity to highlight that your setting of the computer influences the label here. And the same might be true when converting dates that are written like this. So January 31st, you need to have an English locale on your computer. Otherwise, this might not actually work in your case, and you have to spell the month in your own language, and the 31st as well could be different in your language, and then this might not work perfectly. Anyway, back to the plotting. So I made a new column called weekday or wday here. And then I want to create a bar plot using wday as my access static. And what this does, it shows me how many flights started on every Monday of this year, every Sunday, every Saturday, and so on. And we can see that the bar for Saturday is the shortest. There are roughly 10,000 flights less in total on Saturdays. So this is already an interesting pattern that we're seeing here. Then one really great function or set of functions actually that are present in LubriDate concern rounding. How do you round a date? We can have a look at this. So I used date 1 object that I made earlier, which is the 31st of January here. And we use the function floor date to round this. There's also ceiling date, I think. Yeah, ceiling date. And what this does is it uses a smart way to set this date to the first of the month in this case. So I selected month, and now we have the 1st of January 2017. You can also do this with week. So the 29th now. And we can do the same thing with sealing date. And you can see that now it's the last day of the week. I'm actually not sure what's counted as the first and the last day, so maybe let's have a look with W day. And we also have to add the label. So the first day is apparently a Sunday. And what's the last day? Oh, this is also a Sunday. So, yeah, that's a bit weird and inconsistent here. I would have guessed that the last day is then a Saturday, but it seems that floor date as well as ceiling date selects Sunday, although this is 1 week apart, of course. So why is this useful? As I said, this is basically rounding a date. So what we could do here is instead of W day, we could use floor date. And let's first select day here. So day doesn't do anything to the date. It is basically just it is basically just to show you the default. And what we did before when we wanted to show this over time, we used geom frac poly, but this time I want to use geom line. So basically, since we've done the rounding ourselves, we can use geom line instead of relying on the binning in the other function. But I also then need the actual values, so we use count. And then I map n to the y aesthetic. And now let's have a look. So here we have an absolutely wild up and down because it now uses every single day in here, and on some days, as we've seen before, we have quite a spike, or we have a lot lower number of total departures. So this looks a bit wild, and we can use the floor date rounding to make this look a little bit smoother. So let's put in week here. And as you can see, the line is already a lot smoother because now all values for a specific week are put together on the first day of them. So we have all of them. So we have all dates clustered together on Sundays, and this makes the line look a lot smoother. If we had a longer data set, it would probably make sense to do the same thing with month, though we rounded together all dates on the first of the month. Here it looks a little bit weird, but we can see that there's a sharp drop in February, and this is probably because February has fewer days, so there are 3 fewer days in here, and we see that the drop isn't actually that big. The problem here is the y-axis, which only reaches from 25,000 to 29,000, and right at the bottom here it is only a difference of about 2,000 flights, which makes sense when you look at the numbers. So usually you have roughly 30 days in a month, and you have roughly 30,000 flights, so about 1,000 flights on a day, and then of course the 2,000 flights difference makes sense. If you wanted to have a different y-axis here to make this look a little less dramatic, you could use scale y and then continuous, and here you can enter the limits of the y-axis, so this needs to be a vector of 2, and we could set it to 0 because theoretically 0 flights in a month is possible. And then as the top one, we have around 30,000 here. And when you look at this now, you can still see the dip, but it's not as dramatic as before. Lubridate also provides you with a function that's called update. And what this does is basically change individual components of a specific date. This can be sometimes useful if you actually entered the wrong date. Usually I would prefer to replace the date, but you can also use update. And the way this works is that you enter the individual components here. And if we have a look at date 1 first, so that is the 31st of January 2017. And we could, for example, update the year here. Then we have the same day, but in a different year. And as you've just seen with the code I've already copied in here, you can also update the month, day, even the hour. Once you do this, you obviously transform this into a date time, but you can see that you have now basically a completely different value from the observation that you've updated. The book names one interesting use case for this, and it is the only one that I could think of. Namely, you could update, you could basically recreate the floor date command by using update and setting all of the days to 1 here. And as before, this basically rounds the dates, and what we've done here is to set all of the days in the departure to the 1st of January. So that means that we have basically now the sum of all departures at a specific daytime. So at 6 o'clock here, you can see there are a lot of planes leaving. Between midnight and 6 o'clock, there are only no planes leaving. This is probably because there are certain laws that prohibit planes from starting, but then there are individual airplanes which have special license to fly at night. So you have a very slim baseline here between midnight and probably 1 o'clock. There's absolutely nothing. There isn't even a line. And then here there are probably very, very few flights which leave at this time, and then it gets really busy once the clock hits 6 o'clock in the morning. And this is basically it when it comes to dates and date times and how you work with them. The book also mentions, though, that you can work with time spans. So let's make a subsection here. And time spans are created when you subtract or add one date to another. And the example that the book mentions is the age of Hadley Wickham, so the creator of many packages in the tidyverse and also one of the authors of the book that we are using. And what we could do here is we could calculate his age at a specific point in time. So we can calculate it for the 1st of January 2020. And when we do this, we get a printout, which is the time difference, 14,689 days. This isn't, of course, very useful. So what Lubridate does with that is you can transform it into a duration, and duration is the first form of time spans that we learn about. And when you put this into a duration, you can see that it transforms it into years and seconds, actually. So you have the seconds between the first date and the second date, and then helpfully you have a display how many years these are roughly, and it changes depending on how big the time span is. So in brackets is always the most useful unit of time that makes you understand what the time span is actually referring to. So as I already said, we have durations, in loop redate. We also have periods and intervals. And the difference between those is arguably very small, but it might be important in some cases depending on what exactly you want to do. So durations are measured in an exact number of seconds, while periods use more human time, which might be important, for example, for leap years, or when you transform from summertime to wintertime in regions where you still have the daylight saving times, such as Europe. And loop redate offers two different sets of functions for this. So let's have a look at durations first. So the durations are always prefixed with a D character. So you know that you have the duration seconds, and then when you enter the seconds here, you get 15. So 15 seconds. When you use D minutes, it transforms under the hood those 10 minutes into seconds, but then displays this as minutes again. So we have 10 minutes. You can input several values at once using the concatenate function, the little c. And when we do this with hours now, so we have 12 hours and 24 hours, you see you have 43,200 seconds and 86,400 seconds, which of course is 12 and 24 hours, or a day here. So it immediately changes to a day whenever you have at least 24 hours in a duration object. So the days here as well. So we have 1 day. So we have 0 days first, which is 0 seconds, 1 day, 2 days, and so on. We can do the same with weeks. You see it is still basically a number of seconds, but now we have the information that this is roughly 3 weeks. In this case, it is exactly 3 weeks, but it doesn't really matter. And then we have the d-year command, which basically concludes this, and we have the number of seconds here that are in an average year. So as I said, periods use human time, as the book calls it. We can quickly make an example here. So 1 p.m. and as a time zone, I use my current time zone, which is Europe, Berlin. As I said, we learn about time zone a little later on. But here we go. I create this daytime, which is measured in CET, so Central European Time. And then the problem arises when I now want to add 1 day to this, and I use the d-day function to say I want to add a duration, so an exact number of seconds to this. It's actually d-days. And as you can see here now, it's actually 2 o'clock Central European summertime. And this is because between the 26th and the 27th in 2022, there will be a change from winter to summertime. And this means that exactly 1 day after 1 o'clock on the 26th, it will be 2 o'clock. Periods are different than that. Instead of adding an exact number of seconds, it tries to guess what you want, and in this case, when we want to add 1 day, it displays the same clock time 1 day after the date of this 1 p.m. object here. The second thing where this difference is important is with leap years. And when you add the duration of 1 year, so the number of seconds of a year, you get the 31st because 2016 was a leap year. And when you add a period to this, you still have the 1st of January. And this is basically the only difference. And then finally, the book mentions intervals. Again, I think this is not hugely important. And the only difference between periods, durations, and intervals is that intervals are created by subtracting a date or a datetime from another date or datetime. So it always has a start point. So for example here, if I simply used years, then I would have a period. But if I start this with a date and then add 1 year, I have an interval. And this is the only difference here. And then one thing we need to talk about is time zones. You can check your current time zone with the command sys time zone. And here it shows that I'm in Europe Berlin time. And you can also list all of the available time zones by using the Olsen names function. I'm putting this into a table here and then viewing it. So we can look at it in the view command in the spreadsheet like viewer. And if you only look at the time zones of Europe, you can see that we have a number of different time zones. Many of them are actually the same. So Amsterdam and Berlin are the exact same time zone, which is Central European time or Central European summer time. But some are different. Dublin, for example, is an hour behind. And then we can look at the difference here. So let's construct a date time using ymd underscore HMS. So we convert the string to a date time and we use the time zone Europe Berlin. You can see at the end you have Central European summertime. And when we now use unclass again, you can see the number of seconds since the Unix epoch, which is saved here. And if we do the same with a different time zone, let's use America, New York here, you can see that this is actually a different date time, but when you look at the normal printing, you see it is still 12 o'clock, but now we have EDT time. We have the EDT time zone. If we wanted to have the exact same value under the hood, we would need to subtract 6 from the time in the string. So instead of 12 o'clock, we use 6 o'clock in the morning. And then we get the same value as if we had used the European Berlin time zone. And this concludes the explanation of dates and date times. As always, I will leave a couple of exercises in this file here, and I hope you didn't get overwhelmed with all of this information in today's session. As I said, these are all things that you don't need very often, and you can always come back to the video or to the book to look something up. I mainly wanted to show you that strings, factors, dates, and datetimes have a couple of quirks that you should be aware of when working with them. But as I said before, mostly you can get around your data science projects with the things that we've learned in the first couple of sessions when it came to plotting and data transformation and tidying data. And with this, I leave you for today, and I'm looking forward to see you next time. Bye bye.